The electric vehicle industry is increasingly moving toward integrated battery packs that blend two distinct chemistries, nickel manganese cobalt, or NMC, and lithium iron phosphate, or LFP. When these mixed architectures reach their end of life, they present a major challenge for the global recycling supply chain. Standard mechanical crushing and sorting processes are unable to cleanly separate the NMC and LFP components once they have been commingled. The result is a chemically complex, inseparable powder known as black mass. Historically, recyclers have viewed the LFP in this mixture as a severe contaminant. Specifically, the iron and phosphate from the LFP are known to interfere with the recovery of high-purity nickel and cobalt precursors. To strip the metals from this mixed mass, industrial plants typically use a combination of sulfuric acid and hydrogen peroxide. This chemical workaround creates a substantial carbon footprint, as every kilogram of hydrogen peroxide consumed generates over 1 kilogram of CO2 equivalent emissions. However, the LFP in that black mass doesn't have to be a contaminant. From a thermodynamic perspective, it is a powerful reducing agent. The reductive potential of the LFP scrap can be harnessed to replace hydrogen peroxide as the primary driver of the leaching reaction. If the chemistry is managed correctly, the material once labeled as waste becomes the reagent used to unlock the metals trapped inside the NMC lattice. In an acid solution alone, NMC transition metals are resistant to dissolving. They require a supply of electrons to break their molecular bonds. Without an external reducing agent, manganese extraction in acid typically stalls at a mere 34%. This is where the LFP scrap changes the reaction. It provides a natural source of iron 2 ions, which act as electron donors. When the materials make contact in the sulfuric acid, a redox reaction begins. The iron 2 oxidizes into iron 3, transferring an electron out of the LFP structure. That electron is accepted by the manganese 4 in the NMC lattice, reducing it to soluble manganese 2. The same mechanism reduces cobalt 3 to soluble cobalt 2 ions. This transfer of electrons effectively dismantles the entire NMC structure, allowing the nickel, cobalt, and manganese to dissolve into the liquid. By letting the different battery chemistries react with one another, the need for complex physical presorting is eliminated by the chemistry itself. But relying on this internal reaction requires a very precise mathematical balance. This chart tracks the extraction percentages of lithium, nickel, manganese, and cobalt as they relate to the fraction of LFP added to the feed. On the left side of the curve, below an LFP fraction of 0.47, the extraction is incomplete. The recovery fails here because there is simply not enough iron 2 available to reduce the full volume of NMC. However, if the LFP fraction rises above 0.51, the yields collapse just as sharply. This happens because an excess of phosphate forces the target metals to reprecipitate into solid compounds that fall back out of the solution. The optimal ratio is exactly 0.465, where the reduction is maximized but the phosphate levels remain below the precipitation threshold. Reaching these peak yields is a matter of strict stoichiometric optimization, balancing the necessary iron against the dangerous phosphate. Even at the optimal ratio, the iron and phosphate are now dissolved in the liquor and must be removed to purify the target metals. Sodium hydroxide is added to the mixture to raise the pH level to exactly 2.5. As the acidity drops to this specific threshold, solid particulate begins to form throughout the liquid. The iron and phosphate selectively bind together, precipitating out of the solution as iron phosphate. This leaves behind a purified liquid, while the byproducts of the LFP reaction are collected at the bottom. The remaining stream is now a concentrated liquor of nickel, manganese, cobalt, and lithium, ready for precursor synthesis. This step effectively isolates the former contaminants, transforming them into a recoverable, industrial-grade secondary product. Tracking the mass balance lets us compare the efficiency of this co-feed method against traditional processes. This Sankey diagram compares mass flows. The top traditional route relies on hydrogen peroxide. The bottom route replaces this with LFP scrap. Both output purified graphite and recover nickel, cobalt, and manganese precursors. Crucially, the LFP integrated route adds a third valuable stream, recovered iron phosphate. The yields of the two processes are nearly identical, but the LFP-driven method avoids 1.7 tons of CO2 equivalent emissions for every ton of NMC processed. These environmental savings are critical for meeting the European Union's 2030 mandate, which requires a 70% recycling rate for all battery materials. The official EU calculation standard excludes baseline oxygen and carbon from the input mass. Recalculating the mass to account only for metals significantly changes final recovery percentages. Under these metrics, the LFP co-feed process achieves an overall recycling rate of 88%. The result is a process that separates complex waste into distinct high-purity materials. By utilizing the internal chemistry of mixed battery scrap, recyclers can bypass the environmental costs of peroxide while meeting the strictest recovery standards in the industry.